Welcome to my flash talk about our recent work on temporally modulated non-Hermitian optical systems. So what do we mean by non-Hermiticity, and more specifically temporal non-Hermiticity? As you know, Hermitian systems are closed systems that do not exchange energy with their environment. Examples of this kind of systems are lossless waveguides or cavities. On the other hand, if we somehow open the structure and allow it to exchange energy with its surroundings through radiation or material absorption or amplification, we end up with a non-Hermitian system. Examples could be leaky wave antennas or absorbers. Now assume that our system is dynamic and we can control the energy exchange in real time. In this case, we say that we have a temporally modulated non-Hermitian system. So you might wonder why we should care about temporal non-Hermiticity. And the answer is that the performance of many static time-invariant systems are bounded by various limits, such as the delay bandwidth, the True-Harrington, the Bodefano, and the Rosenau limit. All these limits put certain restrictions on what we can achieve in a static structure in terms of, for instance, bandwidth, size, or quality factor. And in this study, we aim to explore how we can use temporal non-Hermiticity to overcome some of these limitations. The first question that we try to answer is whether we can bypass the delay bandwidth limit for a bound state in the continuum. Bound states in the continuum are unique in the sense that even though they are open, they do not radiate. So they have diverging lifetime. But due to the delay bandwidth limit, they must have vanishing bandwidth in the static case. So by using a time-varying epsilon near zero shell, we showed here the first demonstration of critically coupling a broadband pulse into a bound state in the continuum. Another relevant question we had related to temporal non-Hermiticity was about whether we can mold the spectrum of a temporal modulation in some useful ways. And once we develop a theory for the temporal scattering series, we will realize that there's a special case when the Fourier spectrum of the modulation is one-sided or causal, as we name it here. Specifically, in this case, we see that the output frequencies cannot precede the input frequency. And since the math is essentially the same as for the case of causality in the temporal domain, we derive what we have called the anti-Kramers-Kronig relations to determine the condition to achieve this one-sided input-output relationship in the spectral domain. And this concept could be useful for several applications. First of all, since the output frequencies do not precede the input frequencies, we have no phase conjugation, in other words, no reflections. Here, by exploiting this, we have designed a broadband absorber with dramatically reduced reflection compared to its spatial counterpart. Another application could be the cloaking of a temporal event, such as a permittivity perturbation, which normally would induce scattering for an incoming wave. Now, by adding the anti-Kramers-Kronig pair to it, we basically guarantee that the scattering is reduced. A final example of this concept could be the ability to achieve one-way transport along a synthetic dimension, for example made of the modes of a ring resonator. All these applications might be useful to achieve optical isolation, radar absorption, or robust propagation. And for more information, you can refer to the following publications.